All right, so we'd like to welcome you all to our lab tour today. We hope you'll enjoy it. We're going to start with some introductions and then we'll do a video of our lab tours and then answer any questions that you have. So I'm Mary Brewer. I'm one of the academic and career advisors in electrical and computer engineering. And also I am the proud faculty advisor for our ambassador team, for our student ambassadors. So I am going to let them introduce themselves. We'll start with Kristen and then Max and then Schlock. So I'll let them introduce themselves and tell you their major and what year, and then we'll get started with the video.
Perfect. Yeah, my name is Kristen Harrell, and I am a junior in computer engineering with a focus in controls, robotics, and autonomy.
I'm Max. I'm a junior in computer engineering, also studying with a focus in controls, robotics, and autonomy.
Hi everyone, I'm Shlok Agarwal. I'm a junior focusing double majoring in electrical and computer engineering with my focus in controls, robotics, and autonomy and machine learning.
Awesome. Thank you. So we will get started. Let me share my screen here.
Welcome to the ECE Integrated Design Studio. My name is Richard Gibbons. I'm going to be your tour guide today and take you through some of the cool projects that students are working on. So what the ECE Integrated Design Studio is, it's really two labs. So you have the Autonomous Mastery and Prototyping Lab, or the Amplab, on this side. This is where students can come in and basically build whatever electronics projects they want to build, and the department will actually pay for it. So if you want to explore or build something that's really exciting and interesting to you, you have freedom to do so in this lab. And then on this side, we have what's known as the Major Design Experience. So as one of your requirements for graduation in ECE, you basically have to build a project. And so usually we have a list of projects: robot, magnetic levitation, exoskeleton, that you'll come in, that basically you'll go and build, and you'll show off to your professors as well as your recruiters. I'll be showing you guys that later, but for right now, let me take you through the Amplab. So where we're standing right now is actually basically the soldering space. So this is where students can actually go through and assemble different circuits that are basically different boards that they designed. So I think actually, I think Jonathan might be able to better explain. I think he's in the advanced soldering room. So why don't we go check him out and see what's going on. Hey, you got outside?
Yeah, I do.
I'm shooting a video. I kind of want to see what is. Do you think you can explain like what a circuit board is and all that stuff?
Yes. Well, welcome to the advanced solder room. I'm doing a process called soldering with what's known as a circuit board. Circuit board is how we build our electronics in most modern equipment. It's basically a piece of fiberglass and some metal. It's been cut into a specific shape, and then you can attach components to it using something known as solder, which is kind of like the electrical glue that makes circuits work. So this is a little circuit that I designed, and of course it was covered by the Amplab funding. And I'm going to show you guys how to solder on a little resistor. So I'm going to come in and see the kind of component that matches. That R11 right there will work. So I'm going to come in. I'm going to add a little solder to a point like that. See that little smoke, which is always cool. Flip it over so that it's actually on the right side. I'm going to melt that solder, slide it in like that. I'm going to solder the other side like that. Then come in with this magic stuff known as flux, and add a little bit to it, create a little hiss. I'm going to put this down, and then I'm going to wipe it down, get all that excess liquid off.
Yep.
And then we've got ourselves we got a component soldered on.
Wow.
So this is actually one of the larger components you can solder. That's a surface mount. You can go as small as a component that is so tiny that when placed on a dime, it makes it look like the president's got to sit on it. Some examples are right here on this little practice board we have.
Yeah.
You can see those right there. Those are the ones I'm referring to, called 0402s. We can solder all of these different components that you can find, and you normally need to have special equipment to do this.
Yeah.
See, we've got plenty of lighting, plenty of magnification, which is a must.
Yeah, of course.
Full-on soldering station, reflow oven, dry box, and a stencil plier.
Yeah, that oven's not for baking cookies. But yeah, and so basically this is how a lot of the circuits that you guys will study in ECE here at Tech are actually packaged into actual products, like your laptop, your camera, your smartphone, all those great gadgets. And so I think now what I'm going to do is I'm going to take you over and show you some of the electronics projects that students have worked on here in the past. We have a couple of other stations as well. So like here we have the 3D printing station. So if students want to 3D print a part, instead of having to like pay for it, they'll just come here, load the 3D model, and then they actually get to print it out on the Ultimaker. So you guys can see it working right now. And then of course the other thing that's nice is that we have access to lots of lab equipment. So if you guys look around the lab, you actually see that basically we have like tens of thousands of dollars of lab equipment that we get to use that you only would get access to either in I guess one of your labs for your second or third year here in ECE. And so one project I want to show you is these speakers. So these were actually a couple of students got together and they actually designed the sound system for these speakers from scratch. So they went on the whiteboard, they drew the circuit, they then put it in some software, they actually designed the circuit board for the sound. And so I think what I'm going to do is, I'm just going to play you guys a little bit of song. Of course, I have to play Understand That for Virginia Tech. And so what's great about these guys is that they actually figured out a way to cancel reverberation. So if you know what that is, if you've ever been to a concert, the MC basically, go up to the mic and then, speak into the mic or whatever. Okay, hear it. That's because, sound is going from the mic into the speakers. Speakers coming out with sound that goes back into the mic. And they actually figured out a way to cancel that out. And it was literally just one little component on 2 leads. So in 3 seconds. Yeah, they really wanted to see if they could build high-quality speakers for ultra cheap, and I say they accomplished that. All right, I just wanted to get at least that point. And now, for you guys, I'm going to bring you over to some of the other projects that students have done in the past. So this guy, let's see here, I'll stand here. So this guy is actually what is known as a step percent, which is actually something that Jonathan also developed here in the lab. Where basically the idea is that you can actually, if you take a bunch of really cruddy stepper motors and drive them at a certain frequency, you can actually produce that particular note in music. So what I'm going to do here is I'm going to play you guys a song. Once I turn this guy on. Come on. There we go. And I think I'm just going to hit play. And so what you guys are actually hearing right now is not a speaker. This is actual hum of motors playing music. Now what's nice is that you can load whatever song you want onto this on this machine. And so that's the step percent. And so we also have a couple of other projects here. So like the LED matrix cube, which is a fun one that people like to see. So this student, I think now he works at some sort of secret lab at Microsoft, I forget. But basically he wanted to come in and actually take what he learned in what was then called microcontroller interfacing from one of the classes you'll take in ECE. I don't know what they call it now. But basically you learn how to actually work with microcontrollers to get them to do cool things like control stuff like this. I think we actually went through the math and figured out that for each of these colors, there's like 1,500 different combinations of like colors that you can actually display on this matrix cube. And so then we have a couple of other projects here. So we also have this guy. See your plug in? Maybe not. But basically this is the Nixie tube. I'll set this down. This guy is the Nixie tube clock. If I can find his power cord, there it is. Plug him in. So what this student wanted to do is he wanted to take what he learned in digital design which is another course you'll take here at TAC, to figure out how to display time using this old technology called Nixie tubes. Did I get to see the channel? There we go. Yep, and so you can see here the time I think is pretty, oh, it's only off by an hour. That's right, because of daylight savings. And so basically the way it works is that you have a little resistive element that when you run a current through it, or run enough current through it, it actually generates a glow. Kind of like when you look inside an oven and you're seeing the glow of the actual heating coils. It's the same concept here. And so when you stack different resistive elements and shape them in different numbers, you now basically have a display of numbers. And so this is what this is basically how they would display numbers on big machines back in, I want to say, the 1940s. But yeah, and I think the student did try to get it hooked up with the radio signal for universal time in the US using this little antenna, but I don't think you ever got around to it. And so we also have a couple of other projects here, like we also have the, basically this guy, which is the, I'm trying to remember now, what was he called? Oh, that's right, another synthesizer. So in case you haven't noticed, the student Jonathan, who you guys saw soldering in the lab, likes to go through and basically make machines that make music. And so this is how they actually produce electronic music back in the 1960s. So if you listen to Here Comes the Sun by the Beatles, the first few seconds that sound was actually created by a machine like this. And so what Jonathan did was he basically went through, designed all the analog circuitry that you see here, and then made it work with a music interface that basically plugs, I think, right into here. Or maybe that's the power port. I don't remember. No, wait, there's the MIDI input. It's labeled right there. And you can actually produce music with this thing. So you can hook it up to a keyboard. You can basically turn these dials to make different notes. And then you can actually play them on the speaker. And so here's an example of a board that he did here, where you can see he basically designed all this here in the lab. So all of it was designed, all of it was built, and all of it was paid for in the lab, or in the Amplab. And then we also have a couple of robotics projects as well, like the low-cost rover. So this is something that we have students do, where basically if you're K through 12, you can come into here to the Amplab and you can actually solder one of these guys together. You can hook it up to your phone and basically you can use remote control on it. It's a pretty cool project. I've got one of these in the home. And I think these are one of the newer ones that Jonathan designed. So you can see this one actually uses Bluetooth instead of Wi-Fi. But still the same concept. Basically a motor driver drives this thing around. You can hook it up to your phone. It's a great time. And then what else do I want to talk about? And then we also have graduation cap. So this is a project that was done by one student many years ago. Basically what he did was he took an RGB matrix, or RGB LED matrix, basically a bunch of lights, stuck it inside a graduation cap, and actually wore this to graduation. One of the things you'll notice is that a lot of the projects that you see here, usually there's two different versions. There's the really nice version that the student actually gets to take home, and then there's what you see here. And so basically what's nice with this lab is that you can actually go through, build your project, and then you can actually take it home. I'll probably make one of these, when I graduate. I'm trying to think about what else I want to talk to you guys about. We also have some of these. So usually what we like to do is we like to have you go through and actually solder one of these as part of your training. So that way you can come in here in the lab by yourself and actually solder these components together. And so this guy is actually an FM radio. So if I plug him in with this wire here, oops, or an FM radio receiver like the one in your car. See, it's got the little Amplab right there. And then if I grab, where do the headphones go? Here we go. Now what's interesting about this guy is that I think headphones actually act as an antenna to pick up the radio signal. So if I can get the volume up here. Yeah, you can barely hear it with these guys. Let me see here if I can hold it up to the camera. Perfect song. And so basically, yeah, so you can turn it into different radio stations and you can actually solder this, build this in the lab, and actually take it home. Leave that there for now. And then I think what I'll do is I'll show you guys one more project that actually Jonathan is working on currently, and then I'll take you guys over to the major design experience. Hey, so I noticed you're also working on this project here. The what was this called again? This is the
called the MicroBitX.
MicroBitX.
Something that was originally designed by a guy named Asher Farhan, and it is a high-frequency ham radio transceiver. I was using this as a way to learn a little bit more about RF circuit design, which is a higher level of regular circuit design.
Yeah.
So what I actually have set up is this is my first design version of it, and it didn't work. Everything seems to work, but it didn't work because RF. So what I did is I broke it down into individual components so that I could test each part and make sure that I'm not making some major mistake. Still doesn't work, but what I have done here is I've taken one of these components out and I'm doing a little test on it. So this is called what's known as a mixer. The mixer is kind of like the heart of a RF transceiver. It's what makes an RF, what makes some radios work. And it's doing something called frequency multiplication. So I've got two oscillators that I've built over here. So this one is giving me a input signal to put. I'm feeding that in, and I've got another one here that I can change the frequency of. Oh. Which that frequency is being fed up, is being shown on that oscilloscope right there. And then we can look at what's happening, what's coming out of this system right here.
So let me see if I understand this. So basically, you're simulating radio signals, right, with these two circuits here, that then feed into this little circuit here, which then feeds into your transceiver. And you're also trying to send signals as well.
Yeah. So as you can see, these three markers here are here's our input signal, there's the oscillator signal, and then there's the output. And if I turn this knob, if you watch that display, you'll notice that it moves left and right. Huh. So if I wanted to, I could set a filter on that and just extract that, and now I've got an audio signal that's been moved all the way into the RF spectrum. And that is pretty much, you take some mixers and some amplifiers and some filters, and you have yourself an RF circuit or a radio.
And where are you working after you graduate?
And I've got a full-time offer to work with Lockheed Martin Space Systems. Yeah. And they brought me on because of my ability in circuit design and that stuff that I've learned while I was working in the Amplab.
Yeah, so one of the things that I don't know if you guys have picked up on in the lab is that, you know, a lot of these students go on to build these great projects, and then they go on to work either for these great companies, or, you know, if they're like me, they'll stay here at Virginia Tech and basically work as a grad student doing awesome research. And so that's basically the whole point of the spaces, that students can come in, explore and learn what it is that they want to learn, and then actually show that off to people. And I think now what I'll do is I'll take you guys over to the major design experience, which is on the other side. Hey guys, what you working on?
Hey, so we're part of the Ieee Robot team, and so what we're working on is designing a robot that can compete in a Pac-Man-like game. So what we have going on here is a robot with omnidirectional wheels, so it can translate side to side, forward and backwards, doesn't need to turn or anything. And then we have stepper motors, which are known for their precise movements, so that we can move precisely into, if we're approaching a wall or anything, we have ultrasonic sensors so that we have object detection and we can move around it. And so I'll turn this on really quick. You should see that 3 of the 4 motors are moving. Right now we're in the middle of testing a power issue that should hopefully get resolved soon.
Nice. So, what's this guy over here?
So this is a little arm, and one goal of our project is to pick up some palettes painted with different colors or labeled with different patterns. So for our robot, we are having the vision sensor, so it can differentiate palette with different color or differentiate palette with same color but different patterns on it. And so this is our arm. Once the vision sensor finds a palette, we'll find the right palette for us, and it can pick up the palette. So currently we're doing a little testing with the servo. So we're calibrating it to find the 0 position, 180 position, and 90 position. So after all those get set up, we can start programming and make it pick up stuff.
Nice.
And I can show you a quick demo if you want.
Yeah, please. That'd be great.
Simple movement. And this one, if it gets connected, it still need to be calibrated later.
All right, perfect. Thank you guys. Thanks you guys for sharing. Really appreciate it. Hey, you
guys? Yeah, sure. I'm free.
Yeah, what's up? So I'm shooting a video here, and I'm trying to show some of the MBE projects. So what you working on?
Right now I'm working on the magnetic levitation project for the major design experience class, where the objective is to design a feedback control system to levitate an unstable system by, well, making it stable using feedback compensators to levitate a magnet underneath a sensor and solenoid. So the whole objective is to make it levitate and also be able to reject some of the disturbances and be able to continue levitating underneath it freely.
Can I poke it?
Yeah.
Oh. Oh.
Yeah.
Hey.
Sometimes I'll get back to each other. So there it goes. Oh no. Yeah, it's in the works now. So, but yeah, eventually future works are gonna get to move up and down sinusoidally, and square wave movement with jolts up and down really fast, and hopefully multiple solenoids moving left to right.
Nice. Well, I'll let you get back to it. Thanks for sharing, man.
Yeah, no problem, Richard.
Tony, how's it going, man? You got a sec? Yeah, of course. So I'm shooting a video for some tours. I was wondering if you could kind of share with us, like, you know, what it is that you're working on here, and like what you're trying to figure out.
Yeah, absolutely. So I'm part of an interdisciplinary team for senior design. So we have mechanical engineers working on an actual physical structure for the exoskeleton. And then I work on the power and motors and controlling. So what we have here is the motor that will be responsive to the force sensors. And so the force sensors are for like when the user wants to move forward or backwards, he will actually press his leg up against the shell of the force sensor and it'll actually move the motor. And so not only that, how hard he presses against the shell or the force sensor is how fast the motor will turn. So actually we have a smart position control or a smart speed control. And so that will send a signal from the Arduino to the motor controller, and the controller actually sends the command to the motor to make it work.
Sweet. Can I actually can I try it?
Yeah, sure. Try it. Yeah, and so if you listen closely, you can actually pulse the motor if you wanted to. Yep.
And this guy.
Yep. And so that'd be like going backwards. So now it's turning in the counterclockwise position. I believe it's too fast to kind of really tell, so I have to like keep my hand on the motor. But yeah, so that's kind of the gist of it right now. But when we later on down the line, when we get our encoders in, we'll have smart position and control, and we'll actually have a working exoskeleton that people can wear and walk around.
Perfect. Hey, thanks for sharing, man. Take it easy.
You too.
Hi, I'm Afia. And I'm Kadesha. And we're general electrical engineering seniors here at Virginia Tech. So you're here in the electronics lab where if you plan on studying general electrical engineering, energy and power systems, or micro and nanosystems, you can expect to be here in your junior year working on various labs.
So right here next to us we have one of the lab benches that you'll see across the labs. And here are just some of the tools that you'll be using in these labs. The first is an oscilloscope that you use to measure a lot of your equipment. Second, here is your DC power supply. And then up here is your AC power supply or your function generator. And all across you have a lot of multimeters so that then you can measure a lot of your circuitry.
Yeah, and using these industry grade tools, you can be building circuits ranging from amplifiers, filters, half-wave rectifiers, and we have BJTs, MOSFETs, capacitors, resistors, everything you could possibly need to succeed in your labs. So we hope to see you here your junior year at Virginia Tech. Have a great day.
Hi, it's Kadesha
and Afia,
and we're back here in the power lab. So if you're in general electrical engineering or in the focus of power systems and electronics, then you'll be taking a power lab here at Virginia Tech in your junior year. So here's just a little bit more about the power lab.
So this is what a typical bench would look like. Everyone's lab space looks exactly the same. And so as you can see here, you have some multimeters, you have your oscilloscope, AC sources, and you're not really building a circuit, you're really connecting elements to other elements. So it's a little different in that way, but it's still pretty awesome.
Yeah, so like Afia was saying, you're working with a lot bigger elements here in Power Lab because power just works with a lot of bigger elements like a transistor, a buck boost converter. So you're really just connecting a lot of things together with wires. And, you know, when you come here, your lab will look this messy with all these wires hanging around everywhere. So we hope to see you here your junior year at Virginia Tech.
So we'd like to open it up to any questions that you have for us. If I could get maybe one of the ambassadors to kind of talk about maybe some of the lab things that you do with either lab in a box or things like that in your your sophomore year. So those labs don't necessarily take place in a physical place, but maybe if you can talk a little bit about maybe the boards that you use, the projects that you do for some of those classes.
Yeah, I guess I can talk about that. So one of the classes that you take during your sophomore year is Integrated Design Studio, and they showed, Afia and Kadisha showed in the video one of those labs that you would actually work in. So that's where you have access to like a oscilloscope and everything like that. So that's going to be hands-on work that you're going to do in a lab your sophomore year. But outside of that, in your intro to ECE course, your freshman year, you're going to get a lab in a box kit, and that's going to come with basic circuit design stuff. So it's gonna come with like a breadboard, resistors, capacitors, wires, stuff like that. And that's where most of those projects are based off of. So you're gonna do mostly like intro projects. I'm kind of blanking on all the projects that we did because there was a lot of labs. I don't know if any of the other ambassadors could jump in.
I can talk about also sophomore year. There's the class Physical Electronics, which covers a wide variety of topics in power electronics, transistors, and those sorts of things. And they had a series of small labs throughout the semester where you would take the actual concepts you learned about the properties of transistors, and you would build a circuit using a transistor and say, all right, let's explore these properties and actually see them come to life. And then also in Integrated Design Project, specifically you have a scope of projects you can choose from. I was involved in a smart home where we were taking an Arduino, interfacing with LEDs, photo sensors, Bluetooth modules, and making a small smart home that could control a home environment.
So this is a class that you take in your junior fall semester. It's if you're taking controls, robotics, and autonomy, you'll be taking AC circuit analysis lab. So you'll be using the equipment that you get in your lab in a box to make an ECG machine, which can read your heart rate and different kinds of filters and sound equipment which can produce sounds of different, which can filter sounds and produce different sounds. So which is pretty cool actually. You can actually see the heart rate on a monitor and on an oscilloscope actually. So that's something you should be looking forward to.
Great. So we've got a couple questions in the Q&A, and I don't know if any of our panelists are going to be able to answer this one or not. It says, what types of solder do you have? I don't know if any of you all have worked in the Amplab and would know the answer to that or not. I'm getting no's from everyone. So the Amplab is really the main place where we do have soldering, and unfortunately, nobody's worked in there, so we can't answer that question for you, but we're really sorry.
So I took a tour of Amplab once. It was like 2 semesters back. So over there, I asked these questions. So I think, I'm not, don't quote me on that, but I think it's lead-free solder that we use along with flux. So if that answers your question, that is that. But also you can go into the Amplab and take a tour yourself and ask all of these questions to the people over there.
Yes, definitely. And they do offer regular tours of the Amplab during the semester. So they'll take you around, answer any questions that you have there. Okay, so Lindsay would like to know what percentage of females we have in electrical engineering and the percent of females in computer engineering. So I don't have exact numbers on that, but I can tell you that we are increasing our female population. It's not where we want it to be. We are, I think, around 20 to 24% female now. We used to be, when I first started working in this department way back, we were only at about 10%. So we have definitely increased in that. At one point in computer engineering, we were down around 4 or 5%, and that has definitely increased over the last 10 years. We still have a lot of work to do, and we are trying to increase, but every year we see a little bit of an increase. So like I said, I think we're up to around about 20 to 24% female in the department. So Kristen can tell you we're working on increasing that number, right, Kristen?
Of course, yes.
And Kristen is computer engineering. So we're increasing that a lot. We're seeing a lot of increase in the computer engineering area with females. So we hope that answered your question. Anything else that our panelists want to share with the group that's here about why you're interested in electrical engineering or computer engineering, why you're doing it, and what you hope to do in the future. You want to kind of talk about that?
So before I talk about why I like electrical engineering, computer engineering, I would also really like to mention one more project that you do during your sophomore year. So this is a class called Fundamentals of Digital Systems, in which you get an FPGA board, and by the end of the class, you're supposed to make a simple computer out of that FPGA board. So you're able to do all the mathematical problems. You're able to solve all the problems. You're able to calculate stuff. It's basically a simple computer that you build on an FPGA board. It's literally that small. I'd just like to mention that is pretty cool that we work on that. So going on to why I like electrical and computer engineering. So I've been a computer fanatic for, I don't know, however long as I can remember. So I wanted to be to go to do mechanical engineering initially. So my dream was to build the world's fastest car. So and then I saw Tesla coming up. I saw all of these different firms coming up, making autonomous cars and whatnot. I was like, why not? Like, if we can build something like that, and if we can help our society by building something that cool, and you have fun doing that, then why just not do it? So I shifted from mechanical engineering to electrical and computer engineering. So when in my freshman year, I was very confused as to where should I go, electrical or computer. And then there were these different tracks which you could choose from, which add to your confusion. But at the end of the day, I decided that I'm just going to do both. I'm going to make my own plan, and I'm just going to do both. I don't want to stay in this confusion. And I'm in college, so I'm going to make use of it. I just did both at the end of the day.
Do you still want to build the world's fastest car?
For sure, but I want to build the world's fastest car, which is also autonomous.
Awesome.
And electrical.
Yeah, I guess I can add to that. The reason why I love ECE so much is the different opportunities, specifically at Virginia Tech. There's a ton of different design teams and research that you can get involved with. So there's nothing short of, getting out there and kind of seeing what you enjoy within the department. I know that I've kind of jumped around on a bunch of different projects and also a bunch of different internships, which is also a really nice thing that ECE students tend to have less of a struggle with, is there's a lot of internship opportunities, and most students find an internship by the time they reach their junior year. So I know I've been really fortunate with that, and honestly, I would say that's all thanks to like Virginia Tech ECE department, because there's so many different things that you can really just hop on and just kind of like show your passions and just, really get to know ECE for what it is.
Max, do you want to add anything in there?
Yeah, so I came to Virginia Tech and I looked at ECE because I wanted to do robotics engineering. I was involved ever since back in grade school in a small Lego robotics competition. That got me fascinated. Like, got into in high school, like, yeah, this is definitely what I go to college for and study more about this. So this past fall semester, I got involved with the TREC lab, which does humanoid robotics for emergency response, which is pretty much the exact field I want to be in. So I'm doing really great research with lots of like-minded students, really focused. And this somewhat ties into Lindsay's question, how much time to spend in labs. Like, there's the Amplab where you can do lots of extracurricular projects, make up your own project, your own time, and what have you. I'm doing undergraduate research actually for class credit. So I'm taking it as a 3 credit hour class, and the description is 8 hours required in the lab. Well, project usually requires a little bit more than that. I probably spend more like 9 to 10 weeks in the lab, but it's lots of fun. I would definitely recommend it.
And yeah, adding on to that, so there are different design teams as well that you can be part of. So, and it's funny how easy it is to just find a project that you're interested in and just start a team yourself. Like, the advisors help you through it. The faculty are more than happy to help you create a team and be a faculty advisor on your team. And once you create your team, you basically get another lab to yourself that you can work in. And so all I wanted to say that we spend a lot of, especially me, I spend like 15 to 20 hours in lab for my design team. And beside that, for my undergraduate research, I spend more than 4 hours per week in the lab. So most of my week goes in the lab. And there are many labs at Virginia Tech. You can be a part of any project in any of one of these labs.
And one of the things that Max mentioned about the Amplab that I think is really important is that the Amplab is not associated with a class. It is an extracurricular, and it is it's really a student-run lab. So students will propose projects that they want to work on in the lab, and if those are approved and by the students that are running the lab, then you'll get to come in, you'll get to learn how to solder, you'll get to do all of the fun things in the lab, and the department will help pay for the equipment you need and all of those things. So it's a really great lab that we have for the department, and any student can get involved beginning in their freshman year. So we even have general engineering students working in that lab. So we thank you so much for attending our lab tour this afternoon. If you have any questions after you leave us today, please feel free to reach out and email us. My name is Mary Brewer. You can find my email information on our website on ece.vt.edu, or you can email our advising email at eceadvise@vt.edu. We look forward to hearing from you, and hopefully we'll see you soon at Virginia Tech. So we hope you all have a great day. Thanks.
Thank you.
Have a great day, everyone.